A straight segment OC of length L of a circuit carrying current I is placed along the x-axis. Two infinitely long straight wire A and B, each extending from z equals minus infinity to plus infinity, are fixed at y is equal to minus a and y is equal to plus a respectively, as shown in the figure. See, all the details which we have read out now is everything is present there in the diagram. You can see OC as one element, and along that the current is flowing. They have mentioned about it. A and B are extension where you have it along minus infinity to plus infinity, and it is along the y-axis. Everything is shown. If the wires A and B each carrying a current I into the plane of a paper, obtain the expression for the force acting on the segment OC. So if there is a current carrying through these wires, no, there will be a force acting on the wire element OC also. So what is that force acting on the segment OC? You have to find it. That is the first one. Then what will be the force on OC if the current in the wire B is reversed? So if the direction of current is reversed, what happens to the force on OC? We are supposed to calculate. Now for that, let us consider that let us see that you have a small element of thickness dx. We will consider a small element on the wire. Okay, so on the wire we consider this small element. We say that this small element is dx, and this dx is at a distance x from the origin. So this we are considering. Now at this point, if this is the x at the point, see, on the y-x-axis you have no, so the coordinates of this point will be x0, 0, and the magnetic field due to that point will be equal to, we'll call this as BA. BA will be equal to mu naught I by 2 pi r. It is because the wire carrying current, the magnetic field around a current carrying wire, you will be having this equation mu naught I by 2 pi r. Similarly, at point B also, at A and B, both the points we will be having magnetic field. At the point B, that is B, B will be equal to once again mu naught I by 2 pi r. Now these are the components of BA and BB. Along x-axis will cancel, because see here along x-axis both the magnetic field will be acting along different direction, like it will be acting exactly in the opposite directions, and those two gets cancelled each other, whereas along y-axis they add up to give the total magnetic field. So the total magnetic field B will be equal to twice of 2 into mu naught I divided by 2 pi r, okay, into cos component, no, it is, so cos theta. Now this we will simplify it. So when you are simplifying it, cos theta will be equal to x divided by r. If you get a right angle triangle here, see, cos component will be equal to x by r. So you can write this equation for B as B is equal to 2 mu naught I into x divided by 2 pi r into r. X by r you are substituting here, so that this equation becomes mu naught I divided by pi into x divided by a square plus x square. So this is the magnetic field. If this is the magnetic field acting on it, there will be a force acting on it, and force will be equal to BIL sin theta, or you can say it at I into L cross B. So the force acting on the current element, we shall write that as for a small element, no, we'll write that as a df. So df will be equal to I into dl cross b. It is like I into b cross l or l cross b, you are writing it. So substituting for all the values, you get df will be equal to mu naught I square by pi minus x dx divided by a square plus x square. So dl cross b can be written as dl into b sin theta, and here theta is equal to 90 degrees, and so sin 90 becomes equal to 1. So you are not getting any sin component here. Now simplifying this, the net force acting, if this is the small force acting on that small current element, then the total force acting on the wire OC, so the net force acting on OC, wire OC, will be equal to F is equal to integral of dF. So substituting the value of dF here, F will be equal to, in this, mu naught I square by pi is constant, so we shall write it outside, mu naught I square divided by pi into integral of 0 to L, it runs from 0 to L, x dx divided by a square plus x square. And this, when you are simplifying it, you will get the value for F as F will be equal to mu naught I square by pi into integral value comes out to be ln of a square plus L square divided by a square, and this force will be acting along z direction. Okay, this is the force acting on the wire. Now the second part of the question they are asking here is, if the current is reversed, what will be the force on OC, they are asking. See, if the current in B is reversed, the magnetic field due to the wires will be only along x direction, and force on current carrying wire will be along x direction, will be 0. So here we have written one statement here. See, we have written here saying that y components cancel and x components are retained here. Okay, when you are resolving it, those are the things happening here. But when the current B is reversed, no, magnetic field in both the wires will be only along x direction, and the force on a current carrying will be along x direction, becomes 0. So magnetic field will be only along x direction, and since the magnetic field is only along x direction, if since B is only along x direction, since B is only along x direction, you have F also, F along x direction becomes 0. So this is the answer for the last part.
Hello everyone, so we are given with the question which says two long parallel wires are at a distance of 2d apart. They carry steady equal current flowing out of the plane of the paper as shown. The variation of the magnetic field B along the line XX is given by. So we need to check what will be the variation and how does it look. So let's begin. So we are given with two wires. Let's suppose that these are the two wires, and the separation between the two is been given as 2d. So let's make it over here as, so separation has been given as 2d, and let's suppose a point in general I'm supposing which is at a distance of x from left wire. So from right the distance would be nothing but 2d minus x. So the magnetic field at this point P, so we can write magnetic field due to magnetic field at point P due to left wire, due to left wire. So it can be written as mu 0 I by, since the wire is very long, so for infinite length wire, mu 0 I by 2 pi r. R is the distance of the point P from the wire 1, let's say left wire, or we can say it as wire 1, and this is as wire 2. So distance will be x, and the direction will be, we can calculate it by using right hand thumb rule. So as the current is coming out, so thumb will point in the direction of current, so the finger curling will give the direction of magnetic field. Alright, so at P the magnetic field direction is above, that is J cap. Alright, similarly we can calculate the magnetic field at point P due to right wire. So we can see it over here as, it can be written as mu 0 I. Since the both the wire is carrying equal current, so we can write it as 2 pi. Instead of x, the distance will be 2d minus x. Alright, so, and the direction will be in the downward, so sense, so minus of j cap. So the net electric field at point P can be written as B net at point P can be given as B due to left, or we can let's suppose it as to be B1, and let's suppose it as to be B2 to avoid the confusion. So we can write it as B1 bar plus of B2 bar. Alright, so adding this value, we will get the answer as mu 0 I by 2 pi can be taken out as common, so we are left with 1 over x minus of 1 by 2d minus x. Alright, so in general, if and here it is j cap. So this is the general magnetic field at point P. General equation for magnetic field at point P we have deduced. So let's say this is our equation number 1. So from this we can conclude if x is equals to d, if x becomes equals to d, so we can say the magnetic field, that is net magnetic field, will be 0. Alright, and if x is greater than d, then we can say the net magnetic field will be, so whole of the answer comes out to be negative, and the net magnetic field will be along negative of j, that is negative y-axis. And if x is less than d, so we can see that the net magnetic field on point P will be along the positive j-axis. So using this three result, we will check the options. So for first option, let's check. As we have seen, at x equals to d, the magnetic field value is 0. So at this point, the magnetic field value is 0, and it is true. And for the value that is x less than d, we can see for x less than d, the value of magnetic field is along the positive y-axis. So as we can see it over here, yes, it is along positive y-axis, and for x greater than d, it is along the negative x-axis. Yes, so the middle part of the diagram is correct. Now let's check the left part. So the left part of the wire, as we can see, the current is coming outward, so the direction of the magnetic field on the left part should be along the negative x-axis, but negative y-axis, but it is showing in the positive direction of y-axis. So this option is incorrect, so option A is not correct. And option C, as we can see, the middle part of the section is incorrect, so this option is also not correct. Option D is also incorrect. Now let's check option B. As we can see, as we have discussed, the middle part of the section is correct. Now let's check about the left hand side of the wire 1. So as we can see, over here, the as the current is coming outward, so the magnetic field direction is along minus j cap, that is along negative y-axis. So yes, it is along negative y-axis. And for wire 2, as we have seen that the current is coming outward, so the magnetic field direction on the right side will be upward, and it is shown in the upward y-axis, along upward y-axis. Alright, so this option is the correct answer to this question. So I hope you have understood the concept, and thank you for watching.